Okay, so in lesson 2.1, we really learned about a bunch of different ways to take the derivative with all those derivative formulas. But in lesson 2, we learned some basic applications. So we're going to apply derivatives to, it kind of feels like physics a little bit, because we're, instead of just talking about a function and derivative and second derivative, that's going to be represented by stuff like position, speed, velocity, and all that stuff. So I'm going to show you how all that correlates. Okay, so this is how we typically see it. We see our main function represented by something like f of x, the derivative represented by f prime x, or the second derivative represented by f double prime x. But when we're talking about more of these applications, we're going to represent these a bit differently. So we're going to talk about how these represent position, velocity, and acceleration. So f of x, we're going to write as, sometimes you might see it as x of t, or other times you might see it as s of t. And both of these are going to represent position. So if a word problem is going to ask you about the position of of something moving, then you're going to use just your normal function. But the problem might also ask the velocity. So if you want the function for velocity, you take the derivative of the position function. And you're going to write this as v of t. And as I said, that will represent the velocity function. Lastly, your problem might ask you about acceleration, and that is going to be represented by the second derivative. So the first derivative of the position is going to give you velocity. Second derivative of position is going to give you acceleration, which we represent by a of t. So it's the same kind of functions we've been working with, they're just under a new name. Your main function is going to be position, your derivative is going to be velocity, and your second derivative is going to be acceleration. All right, now velocity is actually interesting because there's two kinds of velocities we think about. So there is instantaneous velocity and there is average velocity. So instantaneous velocity, we're going to be thinking about one time. So let's just say, to generalize this kind of thing, it will be at time t equals a or something, whatever value a is, it will be that time. So to find the instantaneous velocity at time t equals a, it would be f prime of a, or if we're talking about our actual like the new ways I represented the derivative for you earlier, that x of t, v of t, a of t stuff, it would be v of a. So you plug a into the velocity function, and that is your instantaneous velocity. If you're talking about average velocity, it's a bit different. This one, you're going to need two time values. So let's say for between t equals a and t equals b, the average velocity between these two times. So for this, in terms of our general format that we've been seeing lately, it would be f of b minus f of a over b minus a. You should recognize as this the average rate of change formula that we've seen before. This time it's just under the new name of average velocity. And if we're using it under our new notation, it would be written like this, like x of b minus x of a over b minus a. But remember, I said that position could be represented by x of something or s of something, so it could also be written as s of b minus s of a over b minus a. So it's a lot of notation, but basically the way you remember it is average velocity is going to be your average rate of change formula, and instantaneous velocity is going to be just the derivative at that one point. Okay, so to practice this new stuff I just showed you, I'm going to give you a few examples. So here's our main problem right here. A particle moves along the x-axis with a position function s of t equals t cubed minus 6t squared plus 9t plus 4 for the time t is greater than 0, where s of t is measured in meters and t is measured in seconds. So basically what this problem is giving us is we have our position function, and we are told that it only works for when the time is greater than or equal to 0, and we're given our units, which is meters and seconds. So part A asks us to find the average velocity between t is 2 and t is 6. So remember, average velocity means that we're going to use our average rate of change formula, but with the position function. So our formula would be s of b minus s of a over b minus a. And so now let's actually plug in our values. This time we are between t is 2 and 6. So it'd be s of 6 minus s of 2 over 6 minus 2. And so actually plugging in our stuff here, this is a lot of stuff to actually plug into. We know the denominator is 4, that's easy, 6 minus 2 is 4. But now let's actually plug all the stuff into here. And luckily with these problems, a lot of time it's going to be calculator active. So let me just check what I have for here. It looks like we would have, if we plugged in 6, we would get 58. And if we were to plug in 2, we would get 6. So 58 minus 6 is going to be equal to 52. And that divided by 4, and that actually is going to give us 13. And remember, for these problems, because we're given units, we want to write our answer in units. We are told that S of t is meters and t is seconds, so it will be 13 meters per second. And that is part A. Okay, so part B asks us, when is the particle at rest? And the difficulty here is that we're not actually told if we should use position, velocity, or acceleration to actually figure out where the particle is at rest at. But we can figure this out. So, but to do that, we have to actually think, what do position, velocity, and acceleration all actually mean? So position, there isn't really more we could say. It's just a position. If we want to reword it, it's basically where an object is. If we're talking about velocity, velocity is going to be the change of position. So velocity is change of position. And acceleration is almost the same thing, but rather than acceleration being change of position, acceleration is the change of velocity. So with this insight, we go back to our problem. When is the particle at rest? And at rest, if we think about it, that means that it's not moving at all. So position just tells us where it is. That's not telling us about it not being not moving. Velocity tells us the change of position. And if we think about not moving, that means that its position is not changing. So we're actually going to want to use velocity here. So because we need our velocity, first we're going to actually find our velocity function. And so remember, velocity function is the derivative of the position function. So let's take the derivative of our position function right now. So our position function, as it's set up here, was S of t equals t cubed minus 6t squared plus 9t and plus 4. Now we take our derivative of this function, we get our velocity function, so v of t equals, this is all just power rule, so it'll be 3t squared minus 12t plus 9. And so now we have our velocity function, and it says, when is the particle at rest? We said before that that means there's no change of velocity, and so because there's no change of velocity, that means the velocity is going to equal 0. So we're going to let v of t be equal to 0 in this case. So 0 equals 3t squared minus 12t plus 9. And now, like I said, this is calculator active, so we could just plug this in ourselves to a calculator or whatever, but that's not always the best thing to do. Sometimes it's a lot faster to just do it yourself. So a thing we could do here, we could factor out a 3. So it'll be 3 times the quantity, t squared minus 4t plus 3. Divide both sides by 3, we could get rid of that 3. And now we could just factor this. This will be turned into t minus 3 times t minus 1 equals 0. And that just tells us that t equals 3 and that t equals 1. And so we from this, we could find out that the particle is actually at rest 2 times. It's at rest at t equals 3 and at rest at t equals 1. Okay, part C now asks us, what is the velocity when acceleration is 3? So this one is telling us that our acceleration is going to be 3, and we need to find velocity. So the way we approach this problem is we're given acceleration is 3, so what we want to do is find our acceleration function. We're going to set it equal to 3, and we're going to solve for the t value. And then we're just going to plug that t value back into velocity, so we get our answer. So let's go through that. First off, it says when acceleration is 3, so we need our acceleration function. I have saved our position and velocity functions over here. So remember, the acceleration is derivative of velocity. So let's derive our velocity function. And this is just going to be power rule again. So derive v of t, we get a of t. Derive 3t squared, we get 6t. And derive negative 12t, we get negative 12. Derive 9, we get 0. So a of t equals 6t minus 12. Now we are told acceleration equals 3. So we're just going to let 3 equals 6t minus 12. This is the same as 15 equals 6t, or 15 over 6 equals t. And if we want to simplify that, that is the same as 5 over 2 equals t. So we have our t value, but remember, we're not actually being asked about a t value. We're asked to find velocity when acceleration is 3. So when acceleration is 3, we know that time is 5 over 2. We just solved for that right now. But now we have to plug 5 over 2 back into our velocity to find what our velocity is at this time. So what we're going to do, we're just going to do v of 5 over 2. And that is also, again, calculator active stuff. So let me just see what our answer is right here. And this is going to be about negative 2.25. And that's pretty much our answer. If we wanted to do units again, remember this is with meters and seconds, so it's just going to be negative 2.25 meters per second. Okay, this next one's also a bit weird. Part G asks us, is the particle moving left or right at time t equals 2 and time t equals 4? So this one doesn't actually tell us anything about position, velocity, or acceleration either. But I'm going to tell you right now this is going to affect velocity, and here's why. So the particle moving left or right, that's basically, left or right. Velocity is telling us the change in position. So if velocity is positive, that means position is going to be increasing. If velocity is negative, position is going to be decreasing, meaning moving the other opposite direction. So because velocity is change in position, the sign of velocity is going to be telling us position is increasing or decreasing. If position is increasing, aka velocity is positive, we know that it's going to be moving right. If position is decreasing or velocity is negative, then that means that it is going to be moving left. So applying this to our case, we want to know if the particle is moving left or right at these two times. So we just plug these two times into our velocity function. If the outcome is positive, that means the particle is moving right. If the outcome is negative, the particle is moving left. So let's do v of 2 and v of 4. V of 2 is going to be 3 times 2 squared minus 12 times 2 plus 9. V of 4 is going to be 3 times 4 squared minus 12 times 4, also plus 9. Now, we don't need an actual value for these answers because our question's not asking us for value, it's just asking us if it's moving left or right. But we could also find a value if we want to, so let's just simplify this a little bit. So our first term for v of 2 is going to be 3 times 2 squared. 2 squared is 4 times 3 is going to be 12. So this first term is going to be 12. Minus 12 times 2 is going to be the same as minus 24. And then we just have our plus 9. And simplifying this is going to be negative because 12 plus 9 is going to be less than 24. So v of 2 is going to be a negative value, which means that it is going to be moving left at t equals 2. If we're talking about v of 4, however, that's going to be a bit different. 4 squared is going to be 16, and 16 times 3 is going to be 48. However, we have a minus 12 times 4. That's also going to be 48. So 48 minus 48, that's just going to be 0, and that's all going to go bye-bye. We are still left with a plus 9. So because plus 9 is all we have left, that means that we are left with a positive value. Because we're left with positive, like I said, positive velocity means the particle is going to be moving right. And those are our two answers. Sometimes it asks you for justification, and if it does, just remember this. Just write that because v of t, or actually no, not v of t, we will say v of 2 is going to be less than 0 for the justifying left. And in our case for right, it's at v of 4, so we say that v of 4 is greater than 0. And those are our two justifications should they ever ask that. So remember, velocity is negative, then that is moving left, and that's our justification because velocity is negative at that point. If velocity is positive, then it's moving right, and that's our justification because velocity is positive at that point. Okay, this next one's a lot harder to visualize, so I have a poor drawing, which I'll get into in a minute to help demonstrate what it means. But part E asks us, is the speed increasing or decreasing at t equals, this should be 0.5, at t equals 0.5. Yeah. So to determine this, we're going to have to look at both the velocity and the acceleration. So here's the story. So you got this poorly drawn train, and they're just going on their way, whatever, And oh no, there's supposed to be a bridge over here, but the bridge broke. So they're going to have to stop, whatever, or else they're just going to fall into a pit and everyone dies. So what they do is, because they're not going to be able to stop in time, they call the neighborhood superhero to come. And so superhero is going to fly in. He's going to be over here, whatever, or not over here. He's going to be right here, and he's going to push against the train to try and slow the train down so it doesn't actually fall into the pit. So in this case, the velocity of the train is going to be positive because it's moving this way, and the superhero, he's going to be a negative acceleration force because he's an extra force trying to change the speed of the train, and he's pushing this way. So because they're counteracting, their speed is going to decrease. So the train's velocity is positive, the superhero has a negative kind of acceleration. So because velocity is positive and acceleration is negative, the fact that they're differing means that the speed is slowing down. Now let's give a different scenario. What if superhero was not actually a superhero, he's just pretending to be, and what if he's actually supervillain in this case? So he actually flies to the opposite end of the train, and he's going to push the train to actually help it fall into the pit and kill everyone because he's a supervillain. So in this case, the train's velocity is positive, but the acceleration from the supervillain is also positive. So the train is actually speeding up into going into the pit, basically. So this is the kind of way we tend to explain to people why how we figure out speed is increasing or decreasing. So if we actually write this in a math sense rather than a silly story sense, if v of t and a of t have different signs, then that means that speed is decreasing. However, if v of t and a of t have the same signs, then that will mean that speed is actually increasing. So using this for our problem, we want to know if the speed is increasing or decreasing at t equals 5. And these are not the nicest functions to plug 0.5 into, so this is one you would definitely want to use your calculator, so I'm just going to help you out here. If we did v of 0.5, then we would get a, we would get a positive number. And if we did a of 0.5, we would get a negative number. And so because they're differing, that means that speed is decreasing. So we would say that speed is decreasing. And if we needed to provide a justification, we would say that because v of 0.5 is greater than 0, because it's positive, and then we would also say that a of 0.5 is less than 0, because it's negative. So basically, to summarize this up, if velocity and acceleration have the same sign, it is increasing speed, and if velocity and acceleration have different signs, then it is decreasing speed. Okay, so now that I've shown you all the basic, pretty much most of the stuff we need to know, I'm going to go through 3 more 5-part problems with you, just practice everything, and then we'll be done. So, first question is going to ask us, or tell us that let s sub a of t equal this function, and let s sub b of t equal this different function. These are going to be the 2 position functions for cars A and B when time is greater than 0. So part A asks us, how far ahead is car A than car B when t equals 0? So it wants us to know how far ahead the car A is from car B, and so that's asking the position difference of car A and car B. So basically what we're going to do is we're going to plug in 0 to car A's function and car B's function, and then we're going to see how much bigger car A's answer is from car B's answer. So if we do s sub a of 0, our function is 15t squared plus 10t plus 20. So all the terms that have a t are just going to turn into 0. So s sub a of 0 is going to equal to 20. That same thing applies to s sub b of 0. If there's a t, that's going to turn to 0. So s sub b of t equals 5t squared plus 20. They all have t, so s sub b of 0 is going to equal to 20. Now these are positions at time 0. So car A's position is 20, car B's position is 0. So because 0 is 20 less than 20, that means that car A is 20 meters ahead of car B. So the answer is going to be 20 meters, basically. And that's part A. All right, part B asks us, at what instance are the cars next to each other? Now, if we think about it, cars next to each other means their positions are the same. So we're going to set their two position functions equal to each other. So in this case, it would be 15t squared plus 10t plus 20 is going to equal 5t squared plus 40t. If we wanted to simplify this, 15t squared equals 5t squared. That's the same as 10t squared. And 10t on this side, 40t on this side, so it's 10t squared minus 30t, and then plus 20 equals 0. All of these terms have we can divide all of these by 10, basically. So t squared minus 3t plus 2 equals 0. And then we can factor this into t, or not t equals, t minus 2 times t minus 1 equals 0. And from this, we could find that t equals 1 and t equals 2. And that is part B. All right, now I saved our two t values, t equals 1 and 2, because part B actually has a sub-question. Which car is moving faster at these two instants that we just solved for? So basically, which car is faster at t equals 1 and t equals 2? Now to solve this, velocity is actually going to talk about our speed. So when it's asking which car is faster, it means which car has a higher velocity at these two instants. So we need to find our two velocity functions. So S sub A of t is our position function for car A. So V sub A of t would be our velocity function for car A. So taking the derivative of our position function for car A, we would get 30t plus 10. And if we took our velocity function of car B, which is up here, for our position, we would take the derivative of that, we would get 10t plus 40. So now what we just need to do is plug in 1 and plug in 2. So VA of 1 and VA of 2. And then we would need VB of 1 and VB of 2. So VA of 1, plugging 1 into this, we get 30 times 1 is 30 plus 10 is 40. And VA of 2, we would get 30 times 2 is 60, plus 10 is 70. Moving on to car B, VB of 1 would be 10 times 1 is 10, plus 40 is 50. VB of 2 would be 10 times 2 is 20, plus 40 is 60. So remember, these two answers are going to talk about if we're doing time equals 1, and these two answers would talk about for time equals 2. So looking at these two answers to see which car is faster at time equals 1, we need to find the one with the bigger value. Car A is 40 and car B is 50. So because car B is 50, which is greater than 40, that means car B is big. It's going faster at t equals 1. So car B at t equals 1. If we were talking about t equals 2, on the other hand, it would be these two answers. So car A at t equals 2 is 70, and car B at t equals 2 is 60. So in this case, 70 is greater than 60, so car A is faster. So it would be car A at t equals 2. I just realized up here I said car B at t equals B. That's supposed to be at t equals 1. That's my bad. But yeah, those are our two answers, and that's how we solve that kind of question. Now part C is actually really similar to the original part B. This one asks, when do the cars have the same velocity? So part B was wanting us to know when they're next to each other, which meant their position is the same. But now part C, we just need to know their velocity is the same. So we do the same thing, basically. We just set the velocities equal to each other this time. So the velocity function for car A is going to be 30t plus 10. And the velocity function for car B is going to be 10t plus 40. If we combine terms, we'll get 20t is equal to 30, or that t equals to 3 over 2. And that's all C is. Okay, part C actually does have a few sub-questions. The first one is asking us, which car is ahead at this instant? Which means the instant t equals 3 over 2, which we just solved for. And for that, we actually do kind of the same thing as part A, we just want, because which car is ahead at this instant, that's asking which car has a higher position at that time. So we just plug in 3 over 2 to both position functions. So S sub A of 3 over 2 and S sub B of 3 over 2. And these ones are all actually really ugly without a calculator. So all you really need to know is that this is going to be the smaller one. Car A is the smaller number and car B is the bigger number. If you plug into the calculator, you would find that to be true. And so because of this, car B is farther ahead. And that is part C1, CI, or the first sub-question of part C. That's the answer, yeah. Okay, the second sub-question of part C is also very similar. This one wants to know which car is accelerating faster at this time. And so this time we do the same thing pretty much again, this time only with acceleration functions. So we find their acceleration functions, we plug in our t equals 3 over 2, and then whichever one is the bigger number is accelerating faster. So our first acceleration function would be differentiating the first velocity function. So a sub a of t, and I wrote that terribly, but yeah, a sub a of t, that's going to equal derivative of this, so that's just going to be 30. And a sub b of t, that's going to be derivative of this, and that's going to be 10. And now you might get a tad bit confused right here because there's no t to actually plug in any value into, but that just means no matter what value you plug into this, that means it's always going to be the same answer. So no matter what I plug into the car A, it's going to be 30. No matter what I plug into car B, it's going to be 10. So because 30 is greater than 10, that means that car A is accelerating faster here. Okay, so a new problem here. This one says that a worker drops a hammer from a height of 784 feet above the ground. The hammer's position function is going to be represented by S of t equals negative 16 t squared plus 784. And with this, part A asking us, what's the average velocity between 2 and 6? So, if we average velocity, remember this is the average rate of change formula. So we would do S of B minus S of A over B minus A. So for us, this would be S of 6 minus S of 2 over 6 minus 2. That is going to be S of 6 is 208 and S of 2 is 720. Weird numbers, just happened to look at them beforehand to remember this. That's going to be negative 512 over 4. And negative 512 over 4 is going to be negative 128. And for this whole, this question, A3, all of these ones want units. So this is feet, and then it's going to be over seconds in time. So it's negative 128 feet per second. That's our answer for part A. Okay, now part B. Part B asks us what's the instantaneous velocity at 5 seconds. And now this one is a bit different. This one wants velocity, instantaneous velocity. Remember, instantaneous velocity, we want to find the velocity function and then plug in our value. So taking the derivative of S of t equals all that stuff, we are going to get negative 32t. And negative 32t, that's our derivative for, that is v of t. So now we want to know v of 5. So it'll be negative 32 times 5. And that answer will give us negative 140, I want to say. 32 times 5. I forgot to check this. No, it's negative 160. My bad. Negative 160. And in terms of units, it's still velocity, so it will be feet per second. So negative 160 feet per second. All right, part C. Part C is asking us how many seconds until the hammer hits the ground. And now this one is another one where they're not telling us position, velocity, or acceleration. But if we think hammer hits the ground, in our case, that's going to mean the position is 0. We start at 784, and as it falls, the position is getting lower and lower. That means the bottom, or the ground, is going to be position 0. So we're going to let the position function equal 0. So 0 equals negative 16t squared plus 784. And so we just solve for t. So let's add 16t squared to both sides. I wrote that wrong at first, but yeah. 16t squared equals 784. Now let's divide both sides by 16. That'll be t squared equals 49. And let's square root both sides now. So t equals plus minus 7, technically, but we're talking about this for our function, whatever. If you there's not gonna be a negative time. Time is only gonna be positive. We don't have negative time, so that negative 7 doesn't count. So our answer is t equals 7 in our case. All right, part D asks us, what's the instantaneous velocity when the hammer hits the ground? So we know the hammer hits the ground at t equals 7. We just found that. So basically, we just kind of do part B, but instead of at 5 seconds, we're going to do it at 7 seconds this time. So we actually have our velocity function, v of t equals negative 32t. So that means v of 7 is going to equal negative 32 times 7. And this time I actually know the answer. It's going to be negative 224. And because it's velocity, it's going to be feet per second. Not sure if I put the units on the last one, but the answer was t equals 7, so it would just be t equals 7 seconds. That's the two answers for these past two ones. And lastly, for this one, we want to know the acceleration at t equals 4. So to find the acceleration, we just derive velocity. So derive this function right here. We will get a of t equals negative 32. And again, before, when we don't have a spot to plug t into, then that just means this is going to be our value for whatever value of t. So at t equals 4, our acceleration will be negative 32. And now we are doing acceleration, so it's not going to be feet per second. It's going to be feet per second. Or in other words, you could say feet per second squared. And that is our answer for part E. Okay, our last main problem here today. And this one actually takes a slightly different turn, where we still use our ideas of these applications of derivatives we've been using, but we're not actually going to use like position, velocity, or acceleration. They give us a function, we just work with it. So this one says water drains from a 900-gallon tank that starts full, and the volume remaining is going to be represented by this function, which they call v of t equals negative 4t squared plus 900, where t is in minutes and v of t is in gallons. So even though it's v of t, which we typically represent as velocity, this is not velocity in this case. This is just what we call our original function in this case. So keep that in mind. So part A asks, how much water is in the tank at 7 minutes? So this function is representing the amount of water in the tank, it says. So what we do, if we want to know the water remaining in the tank at 7 minutes, let's just plug in 7. So v of 7 is going to equal negative 4 times 7 squared plus 900, which is also negative 4 times 49 plus 900. And this is basically another calculator active problem, of course. So let me just check the answer for you guys, and this is going to be 704 gallons. And that is our answer. Okay, this next one can be misleading, and people tend to do this one wrong. So let's read this one carefully. This one wants to know, when has 484 gallons drained from the tank? So a thing most people would think is, well, this function they gave us, v of t equals negative 4t squared plus 900. That represents the amount of water, so let's just set it equal to 484 and solve for t. But that's not what we want to do. They want to know when 484 has drained, not when 484 is remaining. So we were also given that it starts as 900, so we want to know when 484 gallons has drained. So basically, we just subtract here, and we will get how much water that we actually want to have in the tank left, and that will be 416. So we want there to know when there is 416 gallons in the tank. That was a bit confusing how I explained it. It basically means that the function represents how much water is in the tank, and we want to know how much has drained. So if we subtract how much is in, how much there was originally in, minus how much has drained, and then we will know how much is currently in, and then we could just solve it like normal. So we have our new equation, 416 equals negative 4t plus 900. So let's add 4t to both sides, or 4t squared I should say, and subtract 416 from both sides. I don't exactly remember that part of the answer, so I'm just going to quickly do some, what's it called? The crazy subtraction stuff that not many people like, but off to the side, ignore that I did that. I totally know the answer already. Let's divide both sides by 4 now to get rid of that 4. And we'll get t squared equals 121. Square root of both sides, t equals plus minus 1, but not plus minus 1, plus minus 11. But again, we're talking about over time. We're not going to have a negative time value, so t will equal 11. All right, part C is asking us, when is the tank empty? And so remember our function we're given to us represents how much water is in the tank. So if the tank is empty, there's going to be 0 gallons of water in the tank. So let's just set that equation equal to 0. 0 equals negative 4t squared plus 900. Let's add 4t squared to both sides. 4t squared equals 900. I wrote equals 9,000. I wrote that. Whatever. I can't write. Now I'm just going to restart this. Okay, so part C is asking us, when is the tank empty? So the function we were given is saying that that's how much water is remaining, and we want to know it's empty, so that basically means when 0 gallons are remaining. So let's set that equation equal to 0. 0 equals negative 4t squared plus 900. Add 4t to both sides, we get 4t squared equals 900. Let's divide both sides by 4. We will get t squared is equal to 225. Square root of both sides, we get t equals plus minus 15. But remember, we can't have a negative time, so it's just t equals 15. All right, part D is asking us, what is the average rate of change of volume in the tank during the first 10 minutes? So, average rate of change, remember that's the formula f of b minus f of a over b minus a. And it's in the first 10 minutes, so we're not given actual time values, but if we're thinking of the first 10 minutes, that'll be between t equals 0 and t equals 10. So for our case, we do v of 10 minus v of 0 over 10 minus 0. If we plug that into our stuff, v of 10 is going to be 400. Wait, no, my bad, not 400. It's going to be 500. And v of 0 is going to be 900. And then 10 minus 0 is 10. So that's going to be the same as a negative 400 over 10. Cancel 2 of those zeros. That's just going to give us a negative 40. And if we wanted to do units, this would be gallons per minute. Negative 40 gallons per minute. Okay, last but not least, we have part E. What rate is the water draining at 12 minutes? And now, if we're looking for a rate, that just means take the derivative of like your main function. So, our main function is v of t equals negative 4t squared plus 900. Take the derivative. Remember, this v of t does not represent velocity, so deriving it, we will not get a of t. We're just going to write it as v prime of t. I wrote that bad, but yeah, v prime of t. And if we take the derivative, we will get negative 8t. So, plug in 12, we will get negative 8 times 12, and that will be negative 96. If we wanted units, it would be gallons per minute. And yeah, that's our answer, and that wraps up lesson 2 of unit 2. I want to apologize for any bad handwriting throughout all this. I hope my actual explanations helped make it all make sense. But yeah, good luck with unit 2, and I have tutorial or review lessons for all the other lessons of unit 2. So good luck.